Hello everyone and welcome to the SBG Systems presentation here at the BAM Forum. And today we'll be presenting on how inertial navigation systems are an essential tool to create a roadmap for autonomous vehicles. So joining me today will be Laurent Letout, who is our Senior Business Developer here at SBG Systems for Autonomous Systems, and myself, the SBG Systems Sales Engineer for North America. So for our presentation today, a brief summary. We'll be going over SBG Systems, who we are as a company. Then we'll go into the autonomous vehicle and localization aspect of it. Then we'll jump to the safe and reliable navigation, and then close with how do we solve the challenge of reliable navigation system solutions for the autonomous vehicle localization industry. So let's get started. So a little bit about SBG Systems. SBG Systems is a leading supplier of orientation, stabilization, and navigation solutions. We have a headquarters just outside of Paris, France, in Carrière-sur-Seine, with 2 subsidiary offices, one in Santa Ana, California, and one in Singapore, Asia. With that being said, though, we do have distributors worldwide that represent us in over 40 countries. With that means we have over 800 customers and roughly more than 30,000 inertial sensors on the field today. So a little bit about SBG Systems product line. So we are going to start on the left with our IMUs. Our IMUs are our accelerometers, gyroscopes, and some have magnetometers inside that are calibrated in-house. All of our sensors have IMUs in them, and you can output the raw data from the accelerometer, the gyroscope, and like I said, sometimes the magnetometer. Next to the right of this is all our all-in-one sensors. So as I said, all of our sensors have IMUs in it, but our all-in-one sensors have an IMU and then 2 or 1 GNSS receiver with our extended Kalman filter, all in one box. This outputs your orientation, your navigation solutions, and then also our marine applications we also output heave for. So heave is very critical for the marine applications when working on water. Next, we have our what we call solutions. The reason why we call them this is because you can see in the picture here, you have the black box to the left that has just the 2 GNSS receivers and has our EKF, CPU, all that kind of stuff. And then to the right, you can see this is our subsea apogee IMU. So these are great for when you're either in survey mapping situations or marine applications when you need to install the IMU in a central location separate from your GNSS receivers to still be able to connect to those antennas. With that also is our software, our post-processing kinematic software called Inertia. Inertia is kind of also key for these solutions and these mapping and surveying applications used because it really gives you that centimeter level accuracy that a lot of surveyors are looking for. Finally, we have our services, which I'll go into depth later on, but we have a bunch of support engineers worldwide to help our customers. So let's dive in quickly to the applications that SBG Systems inertial sensors are integrated on. So you can see here on the top left, we are integrated in autonomous vehicles. This is one of our customers, Coastal Autonomous. Coastal Autonomous uses our ELLIPSE D to navigate its completely unmanned and fully autonomous shuttle through Florida. Next to the right, we have survey and mapping. We have a lot of different products and solutions for this industry, as I touched on earlier. Then to the right of this, we've integrated into camera pointing, or that also can include just payloads, so UAV payloads, unmanned vehicle payloads. But for this particular application, picture is from a gimbaled camera on a helicopter. On the bottom left, we are also very involved in the industrial automation systems. So we're used for a lot of agricultural and construction and mining autonomous applications for these using our ELLIPSE series and our Quanta series. To the right of this, you have our UAV navigation systems. SBG Systems is integrated in a lot of different autonomous UAVs and drones, primarily used for the navigation purposes, but also used for survey and mapping as well. And then finally, of course, you have the autonomous shipping and freight industry, which is a very big and up and coming industry and is very well in demand right now. We currently have a specific motion profile actually for this particular application. So a lot of our sensors, or all of our sensors, you have access to motion profiles. And so specifically for our ELLIPSE series, we've made a truck motion profile that also works with all of the other series, such as like Quanta and Economical. But the truck motion profile really helps when you're going around large bends. It really takes into account the slip angle and the curvature radius given by the inertial sensors. So, in theory, how does an INS work? First is the core, which is what is our extended Kalman filter. The extended Kalman filter is a data fusion algorithm tailored to various inertial navigation needs and applications. This helps the INS when it has a GNSS outage, as you can see here. The INS will provide a estimate position and attitude in short term when you have a GNSS outage, and it gets this from the IMU inputs as well as the estimation algorithm, which is the EKF. But an INS just doesn't stop at the Kalman filter. The position, velocity, and orientation are necessary and are so accurate and robust in our products due to the impeccable IMU and GNSS receivers that we use in all of our products. So as you can see in the diagram to the right, this is an example of our ELLIPSE series because the IMU has a 3-axis magnetometer. Our higher end tactical grade and navigational grade systems don't include this magnetometer. They do, though, include the 3-axis gyroscope and the 3-axis accelerometer. This system also has temperature sensors. All of our ELLIPSE series, you can input odometer, and you can input either your own external GNSS receiver or use ours that we integrate in our both N and D series. Finally, you can also input a pressure sensor. All of our ELLIPSE series output in RS-232, RS-422 in CAN, but if you do use our OEM products, that output is just TTL. So how does SBG Systems ensure the reliable and robust sensors that we offer? This is through our inertial navigation calibration procedure. We have developed an advanced calibration procedure that is applied to every sensor we deliver. If a sensor does not pass our rigorous testing, it is merely scrapped. We do not try to recalibrate and we do not try to retest these systems, we just throw them away. These calibrations are able to compensate for the discrepancies seen in MEMS-based sensors. For example, we calibrate all of our sensors over a large temperature range, as you can see here, from -40 degrees Celsius to 85 degrees Celsius. This is because MEMS sensors are sensitive to temperature change, especially on a very extreme levels of -4 degrees and 85 degrees. Each sensor is delivered with a calibration report, as you can see on the top right, stating it has passed all of our tests and shall work within the given specs. Now, with that being said, I'm going to hand over the floor to my colleague Laurent, who will go more into the localization aspects of inertial sensors and autonomous systems. Thank you so much.
Thank you, Jenna, for this introduction. So why do we need inertial sensors and GPS to support autonomous vehicles? As Jenna just explained, INS is a combination of multiple navigation sensors and will be a key component for the positioning of the autonomous vehicle. It is used at several levels of operation in this field, but first let's consider 3D HD mapping. Today, autonomous vehicles rely on extremely accurate high-definition maps for their navigation. These maps are built during mobile mapping operations. Survey-grade INS will be used in combination with other instruments such as LiDARs, cameras to locate objects and then images in the production of HD maps. Second, INS is of course an essential sensor of the localization function of the autonomous vehicle stack. We are talking about real-time localization here, where inertial navigation is not the only component used, but it is a key component of the reference design, without which it will be extremely difficult to realize this function of localization of the vehicle. Lastly, we are also supporting the development of autonomous vehicle while using INS in combination with post-processing software to assess the accuracy and reliability of the navigation system during engineering tests and qualification stages. We'll be focusing on localization today, but first let's start with a quick review of the core function and of an autonomous vehicle software system. This function can be characterized into the four following stages: perception, localization, planning, and control. First with perception, which is how do we sense the world around us. For perception, you will find a variety of sensors for the purpose of object detection and recognition or characterization. Cameras, but radar, LiDARs are commonly used. After that, all the surroundings are well understood. Then we need to know where we are, and that is where the location takes place. The where we are function is usually performed with notably GNSS and IMU fused together to determine an absolute position. This sensor may also be helped by odometry. When you know exactly where you are and you have a good perception of the environment, you can now plan the lead path where to go. That is path planning, which is calculating the best trajectory for next step based on other vehicles, pedestrians, and obstacles. Then, when you have a good idea of next step, the last task is acting on the vehicle controls to steer, accelerate, or slow down the vehicle to follow and the determined path. Even though these are the four key components of a system, we are going to focus now more on the localization part. So how does the localization stack works? It is not only GNSS and inertial, like I mentioned before, but a collaboration and a redundancy between multiple systems. We can distinguish three different ways of positioning for autonomous vehicles. First, relative positioning, where we can look at the lanes and other vehicles in front of us, for example, using cameras and radar. Relative positioning let us stay in the right lane and keep a safe distance with the vehicle in front of us. For example, vehicles that we can even buy today at SAE level 2 offer this type of comfort. But this is not full autonomy. This is only a relative positioning. Tomorrow, to reach higher level of autonomy, we'll be using two other techniques of positioning. First, considering SLAM and map matching, where we will need these high-definition maps we've been talking about before. We are going to localize ourselves by detecting objects that we identify and recognize in the map. That is how the vehicle can position itself within its environment. It is a very good and efficient way to position ourselves in these areas for which we have maps. But HD maps are not going to be available everywhere, and certainly not globally. Also, environment is subject to change, and continuous maintenance and updates of maps is going to be a challenge and costly as well. For these reasons, we are going to use another technology which is based on inertial and GPS, which, by the way, is the only practical way today to easily obtain an absolute position everywhere. That is a very convenient method to use. We tightly fuse inertial with GPS and other aiding systems to obtain a reliable and robust position at any time. This is available almost everywhere, to the exception of indoor situations, such as covered parkings, garage, or tunnels, for example. And that is why we need to swap back to map matching and vision in such circumstances. So that is really what makes the localization layers. They will independently have their own advantages and disadvantages, with also various levels of delivered performance. For example, GNSS INS will offer very good level of accuracy, most of the time below 10 cm in light urban environments or countryside, which is better than the lane level accuracy that we might need. But in deep urban environment, the situation might be different, where drift and errors in positioning at meter level or even higher are expected. That is why the other layers, based on different technologies, will help the system cope with those more complex situations. And typically, SLAM and map matching are welcome to help us here. Another good thing coming with INS and GNSS is the quality indicators. And that is a very important feature to navigate safely in urban environment. That is, in a nutshell, how localization works with autonomous vehicles. Indeed, without spending hours on that topic, this is how we can briefly explain the localization stack. Now let us look into what I was mentioning before as quality indicators or even protection levels, which are going to be important for the safety of autonomous vehicles. This is a challenge now for this industry to ensure safe and reliable navigation. For that, there is the interesting concept of protection level, which is introduced here with the well-known Stanford diagram. The diagram on the right illustrates the relationship between position errors, that relates to accuracy, and the protection levels, which relates to the confidence that we have in estimating the position. Both parameters will be monitored, and in both cases, we will trigger alerts if we overpass certain predetermined limits. And that is, in a sense, how we can reach an acceptable, safe system from the positioning point of view. Sophisticated inertial navigation systems based on GNSS are very good at implementing protection levels because they use redundancy of sensors, GPS, accelerometer, gyroscopes, etc. Of course, the quality of the software fusion is one thing, but the quality of the hardware is another critical part. So the IMU need to be carefully modeled thanks to a good calibration, and we need to check in real time these parameters like the biases, the scale factor, and the orthogonality to ensure that no drift will affect the precision of our positions over time. Such implementation is a mandatory prerequisite to ensure the certification of autonomous systems. As I've been mentioning GPS or GNSS several times, let's now look at how we make that sensor more accurate. There are two techniques that we mainly employ in our industry, which are both designed to compensate errors by differentiation and that we otherwise called augmented services. These two systems are RTK for real-time kinematic and PPP for precise point positioning. And both of them bring their own advantages and constraints in use. RTK on one hand is extremely accurate with achievable precisions at centimeter level and offer convergence time typically under a minute. What I mean by convergence is the necessary time required at initialization to reach the desired level of accuracy in positioning. But unfortunately, RTK needs a dense network of base stations to enable and deploy the service. All of this will make RTK more relevant for cities or populated areas, and on the other hand, less adequate for remote and wide areas. For that, we may use PPP, a technology that comes with a wider range and even global coverage. It is available worldwide. The accuracy of PPP at decimeter level is still acceptable for achieving lane level accuracies, but the convergence time in this case, unfortunately, is less optimum in the tens of minutes. Thankfully, both technology combined with inertial sensors using tightly coupled algorithm will deliver the accuracy and the protection levels that we need for autonomous vehicles. Now, to terminate my part of the presentation, I will show how we address different challenges that autonomous vehicles pose to us. We have categorized them in 3 different areas, as we've seen in the beginning: HD mapping, real-time localization, and then assessing the performance of your system. For HD mapping, SBG Systems offers high-end survey-grade solution that can directly georeference the object and images very accurately that were previously acquired with a LiDAR or camera. Here we have 2 formats, a box-level solution and an OEM package that is mostly used for installing onboard drones, but not only. On the real-time localization range, we will be looking at more compact systems, some less precise but more affordable for volume production. Lastly, for the performance assessment, we propose a post-processing software that we have designed in-house with the same aforementioned tightly coupled algorithm. This software is typically used by our customers to replay offline after the mission the navigation of the vehicle, in order to determine where they need to correct their own algorithm in terms of positioning and orientation. Please note that all our solutions come standard supporting multi-frequency and multi-constellation GNSS. Now, I give the hand back to Jenna for her to detail this product offering.
Thank you, Laurent, for that. Most appreciated. So now I'm going to conclude our presentation by going through a couple more slides. So as Laurent introduced, how do we solve the challenge? One product line that we do recommend is our NavSight Land Air for land HP mapping. So our NavSight solution, you can configure it either with an Apogee IMU that you see here, as well as an Econox grade. So an Econox grade NavSight solution is going to give you the 0.02 roll pitch compared to the Apogee here that gives you the 0.004 roll pitch. GNSS heading for the Econox is going to be 0.05 degrees, but that's GNSS based with a 4-meter baseline between the 2 antennas. As where with the Apogee here, you'll see that we get a 0.008 GNSS heading, and then both of them do the 1 centimeter GNSS position. It does depend on the GNSS receiver, but in all of our NavSight boxes that this does provide that solution. This is also an easy setup and configuration with our web interface. And again, as it says, we have several modules to fit your needs. So here you see the Apogee IMU. We also offer the Econox as well. And then all of these products are very easy to use with our post-processing software, Inertial, that is highly used in the mapping and survey industry. And then the next solution that we offer is our Quanta. Our Quanta is great for both navigation and mapping. It's a OEM version system, so it's really great for embedded systems or integration. So this is the Quanta. We also offer a Quanta Extra. What that means is that there's an external IMU that you can connect to the board compared to having the IMU integrated on the board that you can see here. What's great about the Quanta is that it is a dual antenna system, but you can also use it in a single antenna system. And it has very low power consumption, which is very useful for a lot of these integration systems. It also comes with 1 year free of our Inertial license, which is used in both autonomous navigation and autonomous mapping, as it helps you. It's a useful tool for troubleshooting. So just a little bit of some specs behind the Quanta. So the Quanta for the roll pitch, just the regular Quanta, is going to be about 0.03 degrees with RTK. And post-process, this will be about 0.025 degrees. And then we also have done some testing with both the differences of using the quanta in an aerial application and a land application. An aerial application with just a single antenna, the accuracy for heading is going to be about 0.5 degrees. For a land application with just a single antenna, it's going to be about 0.15 degrees, so a little bit better. With that being said, post-processed heading is going to be about 0.08 degrees. And then, of course, you'll get that horizontal position accuracy of 1 centimeter plus 1 ppm. So next I'll be going into the ELLIPSE series. Our ELLIPSE series is one of our most popular product lines, as it has a wide variety of solutions for different applications. As you can see here in the picture, this is our ELLIPSE N, because it's a single antenna system used heavily in high dynamic situations. So our new 3rd generation ELLIPSE series has a new 64-bit processor inside, one of the best SWaP-C performance in its category for industrial sensors. And you'll see in the next slide, it does have also a very small OEM version. When size and cost matters the most, the ELLIPSE series OEM version is a really great product for that. So both the OEM and the rugged box that you see here has a roll pitch of 0.05 degrees. Has just a GNSS heading of 0.2 degrees. It is much more accurate in with an RTK heading. And speaking of RTK, to the right of this, you can see that we do offer a 1 centimeter level accuracy for position when you are using the RTK real-time kinematics feed solution into our ELLIPSE series. As I also spoke earlier, these systems are either RS-232, RS-422, or CAN bus for the red box. And then we also offer them in the OEM version, and they output just in TTL. So quickly, let's dive a little bit deeper into the ELLIPSE series and inform you guys a little bit more about the updates that we made. So obviously it's a quad constellation, that's what GNSS means, and dual frequency. The dual frequency aspect is really key for jamming and spoofing, as if one frequency is being jammed or spoofed, we do allow the corrections from the other one. So it does help to create that robust data. It also accepts the RTK correction, so if you have a RTK radio or feed to send in the corrections to our receivers, we do also allow this as well on all of our ELLIPSE series that have our GNSS receivers inside. As I was stating earlier, they are calibrated for harsh environmental conditions. We have various motion profiles used, such as an autonomous truck motion profile, UAV motion profile, helicopter profile, to help integration needs. With that being said, we also do have dedicated outputs because we've done car testing. So with those motion profiles, we also offer slip angles and curvature radiuses. Now, also for those who really like drivers, we do have a ROS driver that's available via GitHub. So next, I wanted to dive deeper into the Inertia post-processing suite that I've mentioned various times throughout the presentation. As I stated, it's really great for both post-processing for surveying and mapping, but also great for real-time navigation systems, as it's a really great troubleshooter. So for example, when you're trying to measure the lever arms between the GNSS antennas and your box, once you've done a couple of data runs, the Inertia software will be able to go back and give you that precision level accuracy for those arm calibration systems. But to get the ultimate accuracy, Inertia for post-processing is definitely the way to go. You get that centimeter level data needed through our forward, backward, and merge processing algorithms for ultimate performances. With that, you get access to over 7,000 base stations and virtual base stations. You can also tightly couple your INS and GNSS data through our Fusion, through our Inertia software. And it has a really great, easy, modern interface that a lot of our customers love. Next, as I mentioned earlier on the product slide, our services. So we have a technical assistance team, or support engineers we like to call them, that are available everywhere you are, because they're in Singapore, they're in California at our Santa Ana office, and they're also in France. So our support engineers help kind of guide our customers for choosing the right sensor, as well as the sales engineers as well. They also help with the configuration aspect of when you do buy a sensor, and basically any other kind of assistance when needed. They'll also give you updates as well as our generated email for when we have new firmware to be upgraded into whatever sensor you're using. Finally, each sensor has a 2-year warranty. You can purchase up to 5-year warranty if you'd like. Our support engineers also offer on-demand training through purchase and/or on-site intervention and testing. So this is great for when you're trying to integrate our system for the first time on whatever application you're using. So finally, thank you everyone for joining myself, Jenna McGuigan, the sales engineer for North America, and my coworker, Laurent, who is the senior business developer for Autonomous Systems. If you have any sales questions for either me in the US or anyone globally, you can see our sales contacts information here to the left. And if you prefer to work with distributors, we do have our worldwide network. You can go on to sbgsystems.com and find our distributors page there. So again, thank you everyone so much, and I hope you guys enjoy the rest of the show.